We're starting the drilling optimization and new tech session sponsored by Verify. So the next presentation is going to be a dual presentation from Brandon Dugan and Beau Marshall. Brandon is doing this remotely from outside this venue. So Brandon, you're there?
Yes, can you hear me?
Okay, yeah, I'm just going to introduce you. So,
Thank you.
so Brandon Dugan is a professor and associate department head of geophysics at Colorado Schools of Mine. He holds a bachelor in geoengineering from University of Minnesota and a PhD from Penn State. His research integrates theory, experiments, and modeling to study fluid-solid interaction in the Earth's shallow crust. Brandon has spent over a year at sea on research vessels, and he has earned major honors, including the 2018 Asakio Tierra Prize and the 2017 Outstanding Faculty Award. So today, Brandon is going to talk with Beau Marshall from IMDEX. So I'm going to introduce Beau as well, and we're going to try to merge those two things together. So Beau is an operation manager at IMDEX in the U.S., leading the integrated field service division with over 21 years in surface core drilling. He progressed from a driller apprentice to senior leadership roles. He has managed mineral exploration, scientific, geothermal, and offshore geotechnical drilling projects across more than a dozen countries. Notable work includes the U.S. first offshore wind farm, the Dead Sea drilling project, research in Eastern Africa, and multiple IODP expeditions. So today, both of them are going to talk about IMDEX at the sea, enabling offshore science in IODP3 NSF Expedition 501. So Brandon, please go ahead.
Thank you again for the invitation to present at the symposium. My sincere apologies for not being able to be present, but I'm currently in Bremen, Germany, looking at the cores and doing more analysis from this exciting expedition, IODP cubed NSF Expedition 501, where we were drilling the continental shelf to understand large freshwater bodies that exist beneath the ocean in the continental shelf. I hope some of you are familiar with IODP or its predecessors, ODP and DSDP. And I didn't put any authors on my title slide because I want to point out that this project was really authored by a collaborative process of everybody involved, from the scientists like myself, from the European science operator who helped put together the science team, but also an amazing operational team for IMDEX, Matrix, and Secor to enable and facilitate the science that we did. In the lower right corner, there's a QR code that points you to the expedition website where you can learn more that I'm going to share today. You can also always follow up with me at any time. So again, thank you for accommodating my virtual presentation. And I hope to share some of the exciting science that we accomplished through this wonderful collaboration and continuous communication from operator to scientist to operator to scientist, with everybody having an equal voice to accomplish our goals. So what were we trying to do? We're going to start 60 years ago, shown here on the left, where there were some really exciting observations made by the US Geological Survey when they were drilling wells from Florida all the way up towards Maine and the Atlantic continental margin to evaluate the resource potential of the continental shelf. We had exploration for oil and gas in the Gulf of Mexico. We were looking to see what mineral resources might we have on the Atlantic margin. And as you can see here, there's not a lot of hydrocarbons there. There's water coming out of a drill pipe. And they found something really exciting, 10, 20, 30, even 70 kilometers offshore. Some of this water came up fresh, 1 part per thousand salinity or lower. And that got people scratching their heads, sort of, how did this freshened water get out there? Why is it still there today? And so we can move from the observations to processes. So on the right, we show a model. My cursor here, this is New Jersey, Long Island, New England. Many of us have put together models of how fresh water can go down into the ground on the continent and be driven offshore from sea level cycles going up and down, glaciers advancing and retreating, but there was a big disconnect. We had these observations, we had these process-based models, but we really didn't know how salty the water is, how it was distributed across the entire continental shelf, and what the rock and fluid properties were that we need to do fluid flow models that are done in hydrogeology and the petroleum or energy industry. So Expedition 501 went to collect those data. How old is that water? What are the properties of the sediments that allow flow? And piece together the geologic evolution so we could understand this really exciting system that could provide water to many people in coastal environments. We're not limited to the New England coast, so Nantucket shown here by my cursor, that's where we focus. But Vincent Post put together this compilation in 2013, each one of these dots going all the way from Alaska down to Suriname and Peru, Niger Delta, South Africa, all the way over to the Perth Basin and to New Zealand, are areas where people have either directly sampled fresh water related to another project or interpreted it from conventional wireline logs, thinking about resistivity. Fresh water is much more resistive than salt water. So each of these places is somewhere where fresh water has been interpreted. And if you add it all up on the back of an envelope, you come up with something like 500,000 cubic kilometers of fresh water might be in ocean basins beneath the surface. That's a hard number to comprehend. If you put it in a bunch of Olympic-sized swimming pools, you'd be swimming all the way to Pluto to figure that out. So we were trying to really put realistic constraints on these back of the envelope calculations with a dedicated study offshore Nantucket. All right. So again, just sort of a summary of what we wanted to do. There's a lot of words here, but we'll go very high level. What is the distribution of fresh water and how fresh is it? Is it 1 part per thousand? Is it 0 part per thousand being freshwater drinking water standards? Is it a mixture of seawater and salt water? And what are the pressures? And think about driving fluid flow. How old is this water and how was it recharged? Was it related to ice sheets? We know North America was glaciated in the past multiple times. Does it relate to proglacial lakes? Or is it modern meteoric precipitation on the continent being driven far offshore? When we start to answer these questions, we can get into some really other exciting questions about what are nutrient fluxes through the shelf, what are microbes doing, and just a whole other suite of secondary analyses that really understand how fluids are moving from the continent into the subsurface and exchanging with the ocean. All right, so where are we going to do this? Just sort of a zoom in. For those familiar with New England, this is Cape Cod, Martha's Vineyard, and Nantucket. We're going to look at a northwest, north-northwest, south-southeast transect, and these 3 sites that we drilled during our expedition in 2025. On the right is a seismic interpretation. 0 is sea level, going 800 meters below sea level, and then going 125 kilometers from near shore to offshore. Looking at the seismic data, we see these deep, shallowly dipping sequences, big erosional unconformity here that we believe is glacial, a big picture of what we want to understand. I'll let the cat out of the bag. We're pretty sure that it's glacially dominated, that erosional sequence. I've been looking at those cores in the last week. It's been really exciting. And then the stratigraphic geometry. So what are the packages that allow fluid flow or don't? And we drilled these 3 sites, 112, 111, and 113. But why did we pick these sites? We also had electromagnetic surveys over the same region. Again, think about the resistivity of the subsurface. If we have fresh water in the pores, it's harder to send electrical current. If we have salt water in the pores, it's easier to send the electrical current. And you can see 112 targets this high resistivity anomaly. This is much more resistive than we'd expect from marine sediments. We think that's a lot of fresh water. We wanted to constrain these geophysical interpretations. Then we wanted to look at this transition from very fresh water to more seawater, and then step out and look at the seawater end member. So we had an ambitious goal of drilling into an unconsolidated environment and doing some really ambitious and first time ever done in IODP science operations. All right, so let's look at some of the data. All right, I'm gonna show you a couple plots here. Here's the seafloor, and we're going down to 400 meters below seafloor. This first line is the resistivity from that marine-based survey that I showed you at site 111. This is in the middle. And we see this resistive zone, and that's where we interpreted that there would be freshened water. Well, like many operations, we wanted to run wireline logs. Here we had open holes we ran a PVC liner down there and did the surveying through the PVC liner to protect our tools and prevent loss of the hole so we could get as much data. And just very high level, we see the same resistivity increase, but a lot of structural variation here showing us differences in lithologies and sand stringers and clay stringers. So there's a lot more to observe. Well, what does that mean in terms of the salinity? That's shown here, seawater salinity on the right, freshwater on the left, the shallow section, all seawater. And then we move over at about 100 meters below the seafloor to 4 or 5 parts per thousand, or 1/10 the salinity of seawater for a 200-meter package interval. And then we come back towards seawater salinity. I'll also point out there's a whole bunch of variability here. We think this is contamination. I'll show you why in a moment. And it was really the cooperation of all the operators, the fluid control, the drilling team, the scientists to fix our operations and try to improve those data. I'm going to show you how we did that in real time. And one other thing for those who think about drilling, here's a gamma ray log, wireline gamma ray log. Think about this left sand-rich section, and we're talking beach sands, should be caving in all the time. Right, this is marine clay. We now know this week there's some terrestrial clays in here, but all of this is soft sediments, unconsolidated, unlithified. We would have expected these boreholes to collapse in, be drilling nightmares, be core recovery nightmares. We have 71% recovery in the sands and the clays, even in very thick, shallow sand intervals, and even in deep sand intervals, which raise a question of why are these rocks not rocks yet, and they're still sediments. But again, cooperatively, we were able to keep these holes open and collect the samples that we've been studying for the last week, and we will continue for years. Well, why do I think these are contamination? Here's an example of how we sampled pore water from the cores that we recovered, but we also ran pumping tests in these open hole, unconsolidated environments. In the lower left, here's early in a pumping test. We can see this really dirty water, it's sediment laden. We're cleaning out the hole from all our drilling disturbance. And later in the test, the water gets clearer and clearer and clearer. We measured the salinity on these samples. So here's salinity versus time during the pumping tests. Starts out at seawater salinity and then quickly drops down to much lower salinity in these intervals. And so this is, again, more evidence that there's a lot of freshened water down there. When we get deep into the formation, we see that freshened water. And I can't emphasize enough how amazing it was that we were able to keep these holes open at one point for 48 hours during active pumping without collapsing. I can't tell you what did it, but it was the team, cooperative, talking together about keeping this hole open to do the science. All right, let's look at site 112, which is closer to shore. We'll do this a little bit quicker. Again, here's that resistivity anomaly from the marine survey. It's more resistive. The interpretation that is that it's fresher water. We look at the wireline resistivity logs, and again, we see this bounce out to highly resistive formations, lots of variability, but again, all the way down for hundreds of meters, freshened water signal the resistivity. When we look at the salinity, we see actually more structure here. Seawater salinity going over freshwater, back to seawater, and then again, 200 meters of 1 to 2 parts per thousand salinity, almost meeting drinking water standards after contamination or test treatment for microbes and things like that. And notice this discussion that I mentioned before, we cleaned all this up because the whole team figured out how do we get better samples? And it was just continuous communication between the scientists and the operators of how do we do better. And in real time, from one site to the next, we made this advancement. And again, just looking at the geology, look at this, 75 meters of almost continuous sand, open borehole. We were able to keep it open, get samples. We're cracking them open and looking at them today. Big clay unit tied to this transition to seawater. And then again, massive sand units down at depth that we were able to keep open, pump fluids out of, well log, and get amazing samples to do our science. We stepped farther offshore, where we expected more seawater contribution and less freshwater contribution, a lower resistivity anomaly from the marine data, the wireline logs. So again, some variability, but higher resistivity than we would expect if it was just seawater. And then when we look at the salinity, we see, again, some different structures. Seawater salinity in the shallow section, this clay unit over here, we transition into a freshened water zone. And we come back into this clay unit here or silt dominated unit. We get back to a little bit more closer to seawater. And then we come down at depth, another sand and another freshened water unit. And so we're seeing from very low resolution marine surveys. Now we're getting high resolution understanding of what this system looks like. And it was just because of the teamwork and a lot of dedication and effort and brilliant minds talking and sharing ideas with equal voices. We're opening the cores now, so I can't show anything more than the liner pictures, but I just want you to get a feel for what these materials, sediments were like. Here's beach sand that we saw at the shallow environment, coarse grained shell lag layers. Again, these boreholes we thought would have been collapsing in, but we were able to keep them open and get all our samples. And then we moved down into some of these clay units that we've seen. Here's a nice gray marine clay. And then we step down into these red and white clays that we now have fossil assemblages that tell us these are Cretaceous sediments. They're not lithified. It is clay, it is soft, and it's terrestrial in origin and deposition. Well, and then we step farther offshore. I've mentioned glaciers a couple times. Some of the cores are really exciting. Here's a silt-dominated matrix with a piece of diorite in it, 6 centimeters by 6 centimeters. Here's some more igneous rocks inside of a silt matrix. So there is definitely glacial debris coming out here. These glaciers played an active role in how the system evolved and likely how that freshen water got in there, which we're still trying to understand. Well, so some high level summary that we know now. There is a significant amount of fresh water and freshened water out in this system. It transitions across many different kinds of lithologies, sands, silts, and clays. So that's telling us something about time of emplacement and energy of emplacement, but it's sort of agnostic to what the sediments are, which is really kind of a fascinating head scratcher. Another head scratcher here, we did not find any sedimentary rock. It is all sediments. We found some paleosols, glacial deposits, shells, sands, and muds. We think the glaciers played a significant role in how that freshen water got out there. But some of our data is indicating that there might be some meteoric recharge coming in today, which is sort of an exciting puzzle for us to deconvolve. Our early insights, when we start to look at some of the models we're putting together, there's a pre-last glacial maximum contribution with those ice sheets playing a very large role. Ice sheet before the last glacial maximum, the LGM probably came out and contributed again. Those ice sheets have retreated, and this system looks like it's diffusion dominated today, not a highly flowing or advective system. And we have thousands and thousands of samples to take to do additional research. So a little bit of operational work before I hand it over to Beau to tell you about the success of how the operational team worked together. 93 days of science operation, 74 of them at sea, 873 meters of core recovered with a 71% core recovery. Again, I cannot emphasize how impressed and surprised I was that we were able to do this in these unconsolidated variable lithologies from sands and clays. For those who've talked to drillers, that is not your favorite thing to drill. And the other thing, we did 9 pumping tests. We pumped over 50,000 liters of fluid from the ground, which helps us address this freshen water story. This is roughly 50,000 more liters than have ever been pumped out of an IODP or ODP well before, and it's allowing us to do our science. We did significant logging, and we left 2 observatories to measure pressure, temperature, and salinity that we're going to go back and collect some data from in a few years. And last and most important, we had a lot of regulation and environmental compliance to meet by, and the team worked really well to make sure that we left a minimal environmental footprint and accommodated all the compliance that we needed to succeed on this project. So I'll hand it off to Beau to talk a little bit more about his viewpoints from their operational side, and then we'll be happy to answer any questions that you have. All right, Beau, off to you.
Thanks, Brandon and Beau.
I guess I'll first say to Brandon, thank you for the presentation there. It's kind of tough to follow, so I'll just say IMDEX participated, and thank you. Now, how much time do I have?
You got about 5 minutes.
I got about 5 minutes.
to 10
Okay.
minutes.
All right, so I will. I obviously had more prepared to talk about, but look, it's. I joined IMDEX about 4 years ago, and they were looking to develop or further develop a service model that I found very intriguing, and I really feel that this is something that the mineral industry needs. Yes, we're talking about science here, this project at a mining convention, but there's a lot of correlations that can be pulled from it, and I want to try to draw on that. So, one of the model that the division that I am helping lead in the U.S. with IMDEX is our integrated field services model. And what it is we're trying to form more of a tripartite partnership or working relationship with the drilling company or drilling contractors, resource contractor, and IMDEX. And the three of us working together, how can we make adjustments and can we try to drive efficiencies and improve productivity? Look, I come from the drilling side. I've spent my whole career in drilling services. There's problems out there, right? It happens. I will blow through some of them that I've happened to just have pictures of over the years, but we know that we can help in this area. We want to help the industry with this. So our field model, it really is just a matter of we put an individual, so when a customer has multiple solutions of ours on a project, we put somebody out there, boots on the ground, that is an immediate responder to any type of issue out there. Mud cleaning equipment, drilling fluids, any of your downhole sensors, anything that is in IMDEX's solution set to help try to drive efficiencies. The main thing here is that this model aims to help. We just want to help. We do it in a variety of ways. We do a lot of training. We try to help work with the drill crews. Our biggest one really is drilling fluids. Drilling fluids get screwed up often. They aren't within spec usually. You could still get the hole down, everybody drills just fine. But we've found that when we dial that in and really help keep it consistent, I will show you, I have proof, I have proved it to myself time and time again over the last 4 years that there is an increase in productivity, right? So look, for whatever reason, the human element in things, we get things wrong. To try to blow through this quicker, any of you like to cook, if you don't use proper ingredients, you don't mix them in a certain order, you don't give it certain time, you probably aren't going to like the food, right? Drilling fluids are similar. So for all kinds of reasons, it can get a little messed up. When it gets messed up, it will cause issues and slow down the drilling. Slows down your bid on bottom time, right? So probably I'm just going to keep kind of rolling through this. But this one here, I just want to touch on real quick. Driller wanted to do the mud his way. That's fine, right? The jar in the first picture there on the left shows a separation of the fluids. I take it back out to the site to him. I scoop up some dirt off the ground. I take some of the better mixed mud that's going to be in this little cup here, drop the dirt on top, then put the dirt into the water bottle there that has his sample. All of the cuttings and sand it drops to the bottom, right? So if we don't have a good fluid cleaning program, you're going to wear and tear drill bits, drill pipe, yada, yada. We've been doing this at least 4 different projects in the U.S. I won't necessarily 100% say their names, but I will tell you and try to show you that when we have, and on both of these 2 projects that I'm showing, there was another mud competitor out there that was providing fluids, but they didn't have a person with on-site representation daily. Well, just by having that person out there, there was a 10% increase in productivity on one and 30% increase on the other. We've been rolling this out across the world, and this is what I want you guys to take from it, that I'm talking about a science project today, but this can be utilized in any exploration projects around the world. So I get a phone call back in September 2024. Hey, we want you guys to do the drilling fluids for us. Okay, great. Then they found out, hey, I heard you made a mud mixing system. Well, yeah, I did. I was just tinkering with it, and well, I would like that out here too. And then it morphed into, well, okay, we have this integrated field services model. Maybe that would be the best approach to put out here on this project. We knew that we were going to have some challenges to work through. This is my 3rd IODP project. The first one was in 2009 off the Atlantic coast, or Atlantic City, New Jersey. I vividly recall breaking open the drill pipe on one of those, and we had this artesian of water, and it took everybody on board by surprise. And that's when we first hit fresh water, which led to probably further research and obviously this project. The other IODP project was the Chicxulub impact crater. Super cool project to learn about the asteroid that crashed in here to kill the dinosaurs. This one here, Drilling in saltwater, you're limited to the type of fluids you can use. Obviously, I don't need to tell you that it's remote, so logistics was an issue. We were trying to avoid using any type of fluids that would compromise the scientific objectives. A lot of times they don't like to use bentonite or whatnot. We were limited on storage space on site, and so we used our mud mixing system because it was electric. Most mud mixing systems will use a gas-powered trash pump. That is hazard offshore. The geology, as Brandon alluded to, it's not very friendly to drilling, so that was going to be a challenge, let alone a fixed time budget and weather window to get this done, right? So a lot of planning went into it, but we ultimately just wanted to touch on that. We put a person out there, we provided the drilling fluids, we provided the mud mixing equipment, mud cleaning equipment, and that was actually critical. There was a time when the SRU went down and we weren't recycling the fluids, and trying to drill with the recycled fluid created a lot of problems with fouling up the tooling and slowing down the drilling. We had an engineer out there testing the fluids every day, making sure that they were staying within spec. Our involvement in that, we had daily meetings to discuss what's going well, what's not. Our guys were out there to look over and inspect the equipment daily. The sole focus was keep them operating, right? Do whatever you can to make sure this project gets done and they are productive. I can't stress how helpful this is, but I'll be honest, I think a lot of times they were bored because it actually was going very well. But that's fine, right? I mean, that's what you want. Brandon touched on a lot of how surprised he was that the holes stayed open. I was too. And it was because of magic in a bucket. This particular product here is, it was TP12, which is a trial product that has now been since given a name of Export D+. This was the sole product that was used on it, and I could not believe the amount of sand that it was bringing back out of the hole. Let alone when they had to trip and go back in, it went right down to bottom. They experienced very, very minor sloughing. It was remarkable. For the interest of time, I won't try to touch on all of the things that it does, but you can go onto our website and read about it. I will say though that this product here, I think, was a big ticket, but I'm not going to take any credit away from the drillers. Those Bort Longyear guys, if they don't have the right pump rate, speed, if they don't take care of that hole, they will blow it out. They deserve a lot of the credit. IMDEX drilling fluids does not drill holes. IMDEX does not drill holes. Those guys did, and they deserve a lot of the credit. So to really just try to explain to you why the project was successful, if you fail to plan, you plan to fail. And there was an insane amount of planning and preparation that went into this. Just the teamwork. Excuse me. If you were to take the logo off the chest of every individual out there, you would not have known what company they worked for. It was awesome. And I would like to see more of this in our space in the mining sector. Really, it's just freestyling here, right? So, but for the interest of time, we got through it. There's so much more to share and talk about with this project, but the key takeaways that I want you to have for this is IMDEX has a model. There's issues out there in the industry that we want to try to help and be a part of and sit at that table and be focused on trying to help make things more productive in the drilling environment, working together with resource companies and drilling contractors. And when it does, and when they allow it to happen, meaning drillers follow recipe recommendations and whatnot, remarkable things can happen. And I'm super grateful that we were invited to participate in this. I look forward to being involved in another one, if that happens, which I believe they will. It really changed the game for the British Geological Survey and those that do these projects. They plan on speccing that fluid and having us involved in future ones. So that's very exciting, and we look forward to that. So thank you guys for your time.
Yeah, thanks, Beau.
Right.
Beau, a little gift for you.
Thank you.